The aim of the research under GraphLex is to investigate the process of graphene curvature control by means of external electric and electromagnetic field and the consequent curvature-dependent interactions with molecular hydrogen. The project is coordinated by the Institute of Nanoscience of CNR, part of the graphene flagship European project involving researchers from multiple disciplines and supported by the Marie Skłodowska-Curie Action Individual Fellowship in Horizon 2020. Graphene is a unique material with high potential for applications from high-tech to the biotech. Those capabilities are directly connected to graphene flexibility and electronic properties, as well as to the possibility of controlling them by chemical functionalization. Curvature-related reactivity enhancement was shown, and the curvature control has found several possible applications from hydrogen storage and energy harvesting to biomed engineering. Thus, the control of graphene curvature is of high relevance. As a fellowship holder, I am collaborating with the host scientist Valentina Tosini to perform simulation in the HPC environment at Cineca, the Italian most powerful HPC center supported by the Partnership for Advanced Computing in Europe and Italian Supercomputing Resource Allocation Project. If you write with a pencil and inspect the results under the microscope, you may find a two-dimensional atomic layer of a hexagonally packed carbon atom, single sheet of graphene. The Scotch tape technique that Nobel Prize-winning Manchester group scientists André Geim and Konstantin Novoselov used to discover graphene is very simple. Started with powdered graphite obtained from, say, a AHP pencil lead, it is possible to peel off individual layer of graphene from graphite using commonly sticky tape. When powdered graphite disappears from the naked eye visibility on the transparent tape, you can put it under the microscope and see the pieces of graphene crystal. But what makes graphene interesting? Electrons traveling in graphene behave like if they did not have any mass and move ahead at a constant speed of 1000 km per second. So it is no wonder that graphene usually turned out to be 1000 times better electric current conductor than the copper. Graphene is incredibly strong. To have an idea about graphene strength, one should imagine one square graphene hammock that is no heavier than a cat whisker, but can hold cat weighing up to 4 kg without breaking. Almost transparent. Graphene letting through 97% of visible light, but it is practically impermeable. And the carbon atoms in graphene are only 0.14 nanometers apart, but not even the smallest gas atoms can go through. Graphene flex 20% without any damage, but altering also some other properties significantly. A single four-dimensional atomic layer of graphene is not strictly flat, but bears topographic ripples, which is attributed to its strength and extreme flexibility. But for many applications, graphene needs chemical or structural modifications. Unlike plastic, graphene could contribute to the better environment and protected planet by reducing energy usage and faster and smaller computer chips and electronic, replacing silicon, lighter and stronger vehicles and airplanes, increasing fuel efficiency and safety, and flexible and cheaper solar cells replacing indium not well suited for a mass production. Graphene has a number of possible applications from hydrogen storage and energy harvesting to biomedical engineering. And the functionalization of cold graphene with hydrogen or other atoms gives the possibility to tune its chemical and adsorption properties for storage application, as well as capture and purification of pure gases and mixtures. Hydrogen seems to be a green alternative to fossil fuels because it is the simplest, most abundant element in the universe due to its energy contents 3 orders of magnitude higher than that of petroleum and its benign combustion product water. Because hydrogen is not an energy source but rather an energy carrier, it needs to be produced. It is not freely available in nature. It needs to produce from water, thus renewable, or from other organic compounds. Hydrogen is stored either in high-pressure tanks or in liquid form in cryogenic tanks, which are not suitable for broad commercial application as the energy density is low compared to the energy density of gasoline. Storing hydrogen in that form is also very expensive. The alternative is to use solid storage material for hydrogen storage, which should be safe, lightweight, robust, cheap storage medium. Since no existing systems meet those conditions, much basic research needs to be done to understand hydrogen interaction with potential solid materials. Cold graphene is an interesting candidate for hydrogen storage. An efficient controlling mechanism of atomic hydrogen storage release on graphene with change of its curvature was recently suggested. In fact, bilateral compression of graphene, atomic hydrogen preferentially adsorbed and convexities, but when required, it desorbed by inverting the curvature of graphene. The curved graphene multi-layer system can potentially reach gravimetric density up to 8% at ambient conditions, target set by US Department of Energy, and a reversible store and release hydrogen by external control of local curvature at room conditions with fast kinetics. The problem now reduced to finding the efficient way of controlling the graphene curvature with respect to the molecular hydrogen adsorption-desorption. Graphene belongs to the sorbent materials. When molecular hydrogen adsorbs on graphene via desorption remains molecular and binds weakly on graphene surface with binding energy in milli-electron-volt range. Interactions are governed by van der Waals forces, and hydrogen desorbs at very low temperature, close to the absolute zero, so that at ambient conditions in which vehicles operate, hydrogen is desorbed. In case of chemisorption, hydrogen dissociates into two hydrogen atoms, which need additional energy. Hydrogen binds chemically to graphene carbon atoms with binding energy in electron range, and desorption takes at higher temperature. To record once more again, while atomic hydrogen adsorption is a spontaneous process with a very small barrier, molecular hydrogen chemisorption process is characterized by a barrier height in order of 1.5 electron volts per atom, making kinetic flooding very slow. We propose that curvature manipulation could be used to improve adhesion kinetics, and for this goal, we study graphene curvature control by means of external electric and electromagnetic fields and consequent interaction, curvature-dependent interaction with hydrogen molecule, focusing on the p-desorption to chemisorption reversible conversion. The model system views graphene supercell, best mimicking the naturally corrugated graphene grown on silicon carbide, which exactly reproduces the full symmetry cell of the real system and can be directly compared with experimental data. As corrugation of the model supercell distorts the symmetry of each hexagon, multiple chemisorption configurations need to be found. We consider at least 10 different hexagons for each most stable p-desorption configuration and at least 3 different chemisorption sites in order to map the barrier height of the p-desorption to chemisorption path of hydrogen adsorption, and in addition evaluate the effects of intensity of external electric fields on those processes. Displayed computer simulation shows how p-desorbed hydrogen attached at the concave sites can chemisorb on graphene via inverting of corrugation. To store and release hydrogen on graphene sheets at ambient conditions, one needs to efficiently control its local curvature. One possible solution could be the use of piezoelectric or flexoelectric effects. Piezoelectric and flexoelectric effects are electromechanical coupling between electric polarization and uniform strain and strain gradient, respectively. Piezoelectric crystals are used in lighters, for example, to sparkle a flame. Crystal requirements are to be dielectric and non-centrosymmetric materials. Semi-metallic pristine graphene is not nor piezoelectric nor flexoelectric because it is centrosymmetric. However, after manipulation, via corrugation, doping, deformation, and so, more graphene can behave as a dielectric. We aim to study flexoelectricity in curved graphene to elaborate local curvature control mechanisms with electric field. Alternative is dynamic control of graphene curvature by means of terahertz electromagnetic radiation. Wavelength of this radiation is in range of from 1 to 10th of millimeter, which correspond to the coherent graphene vibration or traveling nano-sized ripples, ZA phonons, producing a local dynamic modulation on the curvature. The energy of terahertz range is less than electronic band gap of non-metallic materials like rippled graphene, and thus terahertz beam can traverse through curved graphene and potentially invert the corrugation sign. The understanding of the dynamical interplay between graphene curvature and the electromagnetic field would give indication of the possibility of electric energy production also by means of induced mechanical vibration of graphene. Consequently, in this part of the project, on-the-fly, direct time-dependent molecular dynamic calculations will be carried out. Molecular hydrogen absorption on curved graphene is a smaller model for the reactivity control study on curved graphene, which in turn allows designing location and distribution of defects of detergents, adatomes, or chemical species built for 3D frameworks. Thus, after smart functionalization of curved graphene, capture and purification of the pure gases and mixtures or weapon detections will become affordable and easy. Thank you for your attention.